We're going to focus on the equations of equilibrium in 2 and 3/4 members today. After we're done, you should be able to apply the equations of equilibrium and recognize 2/4 members. This is a very important topic that we'll use when we talk about trusses later on in the course. As usual, there are more examples and group problems that you should look through in the slides on the course site. And of course, there will be a quiz after this lecture that you should complete as well. So what are some applications of this? Well, remember the ramps we talked about before. Each ramp in this application has a weight of 400 feet. And of course, the ramps are pinned at A, held in position by the cables. How do we determine the forces acting on the pin and the force in the cables? Well, that's not too difficult, right? Because what we need to do is set up a free body diagram and perform the calculations. But what exact calculations are there? What do we mean by performing calculations? We talked about making a free body diagram of that, but we didn't talk about applying the equations of equilibrium to it. Here's another application where an engine hoist or an engine is being raised via a spreader bar and chain in order to raise the engine up. And of course, some of the questions might be, well, how much force is in the chain? How much force is in the spreader bar? How would we determine that? Well, a free body diagram, but then solving that free body diagram via the equations of equilibrium would be the way to answer the question. Let's talk generally about a two-dimensional problem. So a body that has forces that only lie in a single XY plane. When equilibrium is achieved, what that means is the body is not accelerating. It could be moving, but it'd be moving at a constant velocity. Usually we think of the body just sitting still in statics. But the net force acting on the body would have to be 0, and the net moment acting on the body would also have to be 0. And so we would end up with 3 scalar equations. One equation that says all the forces acting in the horizontal direction, or components of forces that act in the horizontal direction, and all of the sum of forces that act in the vertical direction, and all the moments of all these forces and whatever concentrated moments are applied must sum to 0. So the forces in the x direction must sum to 0, forces in the y direction must sum to 0, and all the moments out of the plane about any arbitrary point you like must sum to 0, regardless of what point you pick. That's the interesting thing about the equations of equilibrium to me, is that it doesn't actually matter what point you pick to sum moments about. You should find you will find a 0 sum of moments if the body is static. Now, these are not the only equations of equilibrium you could potentially use. These 3 are independent. They do not depend on one another, and so they will allow you to solve problems. You could actually choose to substitute one of the sum of force equations for a sum of moments equation. And then you'd have 2 sum of moment equations and 1 sum of force equation. Of course, you need to sum moments about some other point than O, but you wouldn't have 4 equations at your disposal. You wouldn't have a sum of force in x, sum of force in y, and 2 independent moment equations. It turns out that other moment equation is a linear combination of these 3 equations. In other words, you could derive it from these 3 equations. You could, add, subtract, multiply, divide the equations together, or multiply by constants and derive that other equation. You only get 3 independent equations out of this. And sometimes it's useful to use 2 sum of moment equations and 1 sum of force equation, but most of the time we'll use 2 sum of force and 1 sum of moment equations when we're dealing with two-dimensional problems. Now, it's really helpful to recognize members that only have 2 forces on them, and let me explain why. It's pretty common to have linkages in our practice. So whether it's a mechanism that's moving or a support structure, 2 force members or linkages that are only connected by pins at either end are exceedingly common. And since they're so common, and there's others that are common too, but that's the most common example, a linkage with 2 pins on either end. Since they are so common, you got to realize there's only 2 forces applied. Now, you could break up the force at either end of the member You can break those forces up into X and Y components, but the interesting thing about it is since there are only two forces on the member, for that member to be in equilibrium, those two forces have to be collinear. They have to lie along the exact same line. And that helps a lot when you're trying to determine the direction of the force at a pin, for example. And you'll see this in example problems quite a lot. Students get confused, though, because they get used to seeing straight links, and they think, well, the force at either end lies through the body of that link, that straight link. And so what the authors of the slides have done here is something very wise. They've drawn a link that is curved and pointed out that even though the shape of the link is curved, that's not what determines the direction of the force. What determines the direction of force A and force B is the fact that this is a two-force member, and therefore for equilibrium to occur, those two forces must lie along the same line. There's no other option. Otherwise, the body cannot be in equilibrium. If you got force on one end of a link in one direction and force on the other end of the link in some other direction, there's no way those two forces can cancel such that the member could be in static equilibrium. So if you ever find a two-force member in some body that you're analyzing, something that's made up of multiple bodies perhaps, just know that the two forces on either end have to lie along the same direction, and they will be equal and opposite in magnitude. Well, of course, their directions would be opposite as well. All right, so are there any examples of this in the real world? Actually, yes. If you look at the component of the backhoe on the left-hand side picture, it's pinned at A and B, and it is in fact a curved link. However, the force at pin A and pin B must pass through pin A and pin B. The line of action of the forces, imagine that there's force in the plane of that link. Well, those two forces, even though the link is curved, those two forces must pass through one another. Same thing with a hydraulic cylinder on the other piece of machinery in the right-hand photo. Since the cylinder is pinned at A and pinned at B, you can think of it as a link, a two-force member, even though this cylinder is made up of multiple components. You've got the rod, you've got the cylinder, there's a piston inside of there, which of course is attached to the rod, but the force through pin A must pass through pin B and vice versa because the cylinder is acting as a two-force member. And that really helps a lot. Now, one thing that's being done here is the weight of the member is being neglected because technically gravity is pulling down. But in both of these cases, typically the force at the pins is so large by comparison to the weight of the member that we just neglect the weight of the member, call it a two-force member, and we're done. And the error in doing that is very small for the vast majority of cases. So this simplifies our analysis. It simplifies the equilibrium analysis of these rigid bodies because now we know the direction of the force at either end of the two-force member. So how do we solve two-dimensional equilibrium problems? Well, first of all, if not given, make sure you set up an XY coordinate system so that you can speak consistently or write consistently about the directions that things are happening, because direction is really important when you're dealing with forces. Next, draw a free body diagram of the object that you're trying to analyze. Finally, apply the equations of equilibrium to solve for the unknowns. And that's it. That's how you solve these two-dimensional problems. Now, here's some important notes. It is actually possible for there to be more forces than you have equations to solve for them. In that case, what that means is that there's extra support usually. That's what it usually means. There's extra support that the body doesn't absolutely have to maintain static equilibrium. Often this extra support is added in because the body is made out of some type of material or a cross-section or shape that could not span an entire length. In any case, you won't know how to solve those problems in this class. I will teach you how to solve those problems if you take strength of materials with me, because if there's extra support, you have to know how strong and stiff the body is to determine how much of the force is distributed to the various supporting positions. So we can't solve these problems just using statics. We have to think of the fact that actually every body, not every person, but every body that we analyze has some flexibility. It can move a little bit. It's kind of like a spring. And so we have to take the deflection of the body into account, and then we'll be able to apply the principles of statics with a deflection equation or two, maybe even more, to solve the problem. The order that you apply the equations may affect how easy it is to solve the problem. It's actually pretty easy to set up a problem and start down a path of solution that's really difficult to complete just because the algebra becomes sort of a nightmare. I don't know how to teach you the way to avoid that. The only thing I can tell you is look at the example problems that I work, think through the problems that you are working for your homework, and make sure that you're thinking about, well, wait a second, once I've set up the equations of equilibrium, is there an equation that has a single unknown in it? If so, I'm going to attack that one first. That way I can get that unknown out of the way and then use it in any of the other equations of equilibrium. So I'll hopefully show you some techniques. I've tried to include a good variety of techniques in the example problems to help you understand and learn how to do this. If you calculate that one of the forces are negative, then what that means is that you simply assume the wrong direction for that force. Now, I'm not saying you assume the wrong line of action. It's just it points in the opposite direction. That's all it means. So you'll see that happen quite a bit in my example problems as well.